Hello everyone, I'm Erin from WebNazar, your digital lens on everything trending. Today, we're diving into another important story, idea, or innovation shaping our world.
Every major AI lab today boasts about a 1 million token context window, but swallowing a million tokens is a party trick if the model's logic collapses the moment you ask it to do actual work. True long-horizon engineering requires an agent to hold the context of an entire codebase, automate multi-step research, and execute complex debugging over hours of runtime without losing the thread. This chart shows how Z.ai's GLM-5.2 performs on these exact sustained tasks. It scores a 74.4 on Frontier SWE and a 99.2 on the AIME math benchmark, proving it maintains strict logical coherence across that massive context. To understand how it achieves this, we have to look at why standard hardware architectures break at this scale. When you expand a context window to a million tokens, the raw floating point operations per second, the flops, required to process attention scores grow quadratically. But compute is only half the equation. You also have physical memory limits on the GPU. At a million tokens, pure computation hits a physical wall, transferring the ultimate burden to the KV cache capacity. The hardware simply runs out of room to store the keys and values generated by the attention mechanism. You cannot brute force your way past this bottleneck. Achieving true 1 million token viability requires altering the underlying math of dynamic sparse attention itself. Here's a standard transformer block stack. We isolate the dynamic sparse attention layer and its indexer. First, it executes dot products to measure token relevance. Then, top case sorting determines sparsity routing. In a standard architecture, this exact sequence executes redundantly at every layer. When you push the sequence length to 1 million tokens, that redundancy compounds. This per-layer indexing explosion destroys compute efficiency. It makes long context inference unbearably slow and prohibitively expensive. To solve this, Z.ai developed index share. Instead of repeating the math, it places a single indexer at the start of a 4-layer block. Layer 1's top K operation is captured as a discrete data packet, then distributed down into layers 2, 3, and 4. Those 3 subsequent layers completely bypass their own indexer dot products and top K operations. They just reuse the routing map from layer 1. By eliminating the indexer operations in 3 out of every 4 layers, the required computational load drops sharply. Decoupling the indexer from every layer results in a 2.9 times reduction in per-token flops at maximum context. This reduction brings the computational requirement of a 1 million token window back within the threshold of current hardware clusters. Expanding the context window only solves capacity. To make inference fast enough for production, GLM-5.2 relies on speculative decoding. This uses a multi-token prediction, or MTP, layer. Think of it as a smaller draft model that guesses upcoming tokens ahead of time, which the main model can then quickly verify. During training, the draft model learns using perfect information, receiving hidden states, labeled H1 through H4, directly from the target model. During live inference, a new variable enters, H5. Unlike previous inputs, H5 is a hidden state generated by the draft model itself. Mixing perfect target